There we go. Okay. Good morning, everybody. Where am I? There we go. We're gonna start off with this synthesis problem that I gave you guys to work on over the last night. So I gave you guys a hint that you need to generate a stipulation on this that this cyclopentane can be your only carbon source. So because of that, we're going to have to generate source both halves of the Diels-Alder. So in order to do a Diels-Alder that kind of mimics this, we're going to need something that looks like these two halves. And then afterwards, we'll do some sort of chlorination. So we got to make these two components here and then do our Diels-Alder reaction. Taking a look at our starting material, there's nothing on it, which means we have to either do a radical bromination or radical chlorination. So I'm going to throw in Br2 and light. You could use Cl2 and light, doesn't matter. From this point, if we throw in a base, we can eliminate and make that first reagent. So NaNH2, or sorry, let's throw in an H. That'll give us one component. If we want to make a diene, it's going to be really similar to making an alkene or alkyne. If you add in Br2, the only difference is you need to make sure you're using a large base in this next step. So something like T-butoxide here will get you to this large base, or this diene here. Merging these two together through a Diels-Alder gets us to the majority structure of our compound. And then from here, just to chlorinate, we'd have to add in something like Cl2. Let's just dichlorinate and get our final product. All right. Any questions on this? If not, we're going to spend the rest of the time looking at the practice exams. Let's start with the fall 2021. I guess they're not practice exams. Previous exams. I'm going to get out of here. Oh, that's spring. There we go. That's the wrong page. Man, really struggling. Oh, wait, no, that is the right page. Okay. So, fall 2020 exam. Go ahead and just cross this entire page out. So, chapter 17 concept, we didn't cover it yet. In fact, you're going to cross out a lot of this exam. So, we are not going to do NMR in this exam. I'm going to talk about what we're going to do instead. So instead, we are going to do a normal mechanism from chapter 12. Nope, that's this one. Man, I'm having a hard time finding these. Like, for instance, if you look at this from the exam one, so exam one in the spring, they covered chapter 2020, chapter 12. So instead of that NMR page, we're going to do just a mechanism page. All right, let's take a look at the page after that. Couple reactions we didn't cover. I'll change some of these numbers. But for the most part, we can go through some of these. So, oh yeah, this one too. Anything else? No, no. Okay. So this top one's a Diels-Alder. We'll make a 6-membered ring. We're actually going to make 3 6-membered rings on this one. The middle one is the one you just made, the one you made. It's got this other ring attached to it. The dienophile portion should end up going downward. And then these 2 methyl groups are on the outside, so they're also going to end up downward and should give you this structure here. Let's see. These electrocyclic reactions. There's a bunch of them on this page. Okay. So we have 2 double bonds, which means we're going to make a 4-membered ring. We are in light. So we'd have a pattern of 1 electron on the top, 2 on the bottom, 1 on the top here. Which means they are going to rotate in the same direction. Oh no, sorry, opposite directions to go towards each other. So when they rotate opposite directions, this one's going to get pushed up. This one will get pushed down, and they should end up anti to each other. Next one, we got 3 double bonds, so you can make a 6-membered ring.
Doesn't matter which one you put on the dash and which one you put on the wedge.
Nope, because you have the plus minus.
Okay.
All right, same thing. We got six orbitals because we have 3 double bonds. First one's going to be on the top. Next 2 on bottom. Last 2 on top. Final one on bottom here. Isolating it. We have top and bottom. And then quite a few things. So we are rotating the same direction. That's going to push this one down, this one up, and then this little methyl group down here. So methyl and isopropyl should end up the same. I'm going to draw them both as wedges, or sorry, dashes. Wait, how do I do this? Yeah, this one. And then ethyl gets pushed upward. All right, so HBr at higher temperature is going to have resonance. Let's see. Taking a look at our 2 different double bonds here, it's either going to add to this position or this position. Or sorry, we're either form a carbocation at one of those 2 positions. Seems a little off. That position. One of them is tertiary, one of them is secondary, so you're more likely to form it on the tertiary one. Our first step. And then from here, comparing the double bond stability, this double bond versus this double bond. We have a secondary one on the left, a tertiary one on the right. So the tertiary one's the more likely one to form the product. So this should be our bromination reaction from this. All right, so we're doing a Diels-Alder on this one. It's going to be able to be controlled by resonance. So we can kind of do a quick resonance check. This is going to end up giving us this positive at the bottom. Same thing with this one here. Both the bottoms line up, so that makes sense. We don't need to flip it over. This should basically do its Diels-Alder as drawn. So we're going to end up with a 6-membered ring. We got a bridge head on this one. Oh, that's not 6. Our OME is on the outside. That's going to end up going down. And then we want the, I mean, for this one, we have a little bit different than normal, but we want the largest groups on our dienophile to go away. And then this one methyl, because there's 2 of them there, one of them has to be going forward. Should give us this answer. Same thing on the next one. We have the same configuration. So we're gonna end up with a plus here. And a minus here. They're both on the bottom of their molecules so that they don't need to be flipped over. We've now got a triple bond, which is going to eliminate a lot of our stereochemistry. And should give us this product. All right. Going. What's up?
Why isn't the right part on a dash or a wedge?
Because it's sp2. So because you have a double bond still,
Okay.
because we started with a triple bond here, it's sp2, so it's trigonal planar. It doesn't have any sort of stereochemistry.
And then for the one on top of that, could I draw what you draw on top on the bottom? The top right and bottom. Could I just like flip them?
This portion?
Yes.
So if you flip them, it's gonna disagree with your resonance that we did over here. That's gonna give you the wrong answer. Because your charges are lining up here as opposed to here where they don't line up. This will give you the wrong answer.
Thank you.
You're welcome. Another question in the chat. Oh, you're welcome to draw them in either 2D or 3D. If it's a 6-membered ring coming together, I would prefer it in. Honestly, I'll take it either way. I'm not going to mark it down for it. So you can draw it in 2D or 3D, depending which one you're more comfortable with. All right. Minus 78 means there's no resonance. So this one's going to be a lot more straightforward. We're just going to pick up the H, negative carbocation. Cl can come in. And then we'll do a 1-2 addition. And because this is symmetrical, you could do this on the top or the bottom. It'll give you the same answer. Okay, doing a couple of these ring closings with light. Man, this is a hard page. Sorry, with heat, not with light. We got 8 orbitals, so it should make an 8-member ring. We've got pairs of 2. So first 2 are on top. Second 2 will be on bottom. Third 2 will be on top. Last 2 will be on bottom. And kind of squiggly this guy. Take a look at the 2 endpoints. One on the left or one on the right is on the top. One on the left's on the bottom. Gonna push this one down and this one up. They should have anti to each other. Like so. All right, so I'm making a big ring. This is a 10-membered ring. Kind of looks like two cyclohexane rings together. Shift this one over. We're gonna make a ring that looks like I need better than that. So let's see, we made a double bond there, 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 there. We need methyl groups here, here, and here. Okay. I'm gonna erase some of this. Just gonna draw my orbitals in this one. We've got 10 of them. First two are on top. Next two are on bottom. Top, bottom, and top here. So our two endpoints are both on top. Rotating them both inward, pushes these both up or both down. And that's going to give us our syn product. Okay, this was a brutal page. I'm not going to make your guys' this hard. Yeah, this was just really long. So you might get a couple of these questions. There's also going to be stuff from like 12 and 13. I don't know why this is basically almost all entirely 16 on this page. But the fall of 2020 was the first, I guess, the first actual semester of COVID, and I don't know, it was pretty rough. So the spring exam, I would say, is a better example of what you should expect to see. Let's go on to the next page. If nothing else, I can tell you what to cross out here, which is a lot of these. Let's do some of these ones on the bottom. So, really what we're looking for on this first one is this stereochemistry here. So there's really only two answers for this that are logical. You can either make rough. We can either start with this or this. You either have them cis to each other or trans to each other. You could switch which one is cis and which one is trans would still be correct. We're using heat, so we're just gonna have to determine which one is gonna give us this syn product and which one will give us a trans product. So we can take a look at these, kind of isolate them. First two orbitals on top, second one's on bottom, next two are on top, bottom, top here. I'm just gonna kind of use this to do it. So if I rotated this one, these two towards each other, that's gonna push these both in the same direction. They both go upward. So that means that this would give me the syn product. If I did the same thing over here, I can just draw in those orbitals. I know what they're gonna be now. One of these would go up, the other one would get pushed down. This will give me the anti-product. So with that in mind, I can fill in my 6-membered precursor with these two, both trans. All right, we're just looking for a dienophile portion here. Should just be this. Don't really have to worry about the stereochemistry there or syn to each other, so it should be a cis double bond. All right, for these last ones, what I usually tell people is the best way to do these is to just guess and check. So it's either going to be heat or light. Those are the only two options for this reaction here. Do the reaction with heat, see what you get. If it's correct, heat is the answer. If it's wrong, light will be the answer. It's basically a true or false question. So taking a look at this, we can pull orbitals. We're pretending like it's in heat. So we're going to use pairs of 2. If I isolate those, it's a little wider. Right one should be on top, left one should be on bottom. Nope, wrong way. It's going to push up this methyl group down. Heat would give me this product. So my answer here is light. Doing the same thing over here. Just fill in the orbitals. They are both on the top. that is going to push this one up and this one down, which would give me the correct answer, which means heat is the answer for this one. Any questions on this page? All right, let's take a look at the next one. You can go ahead and just cross off. Where'd it go? There's. Whoops. Didn't learn how to do this one. But we do know how to do this first one. So this is similar to the synthesis we talked about today in class. If you read the instructions, all carbons must be derived from the starting material. So we're going to have to make both the diene and the dienophile out of the starting material. We're making something pretty similar. We really need to just make this plus this to do our Diels-Alder. And then some sort of MCPVA to get to our final product. So first step is going to be, you can do this by an E1 reaction. There's also a couple other options. E1 is probably the quickest, so H2SO4. Now we're doing the same thing we did earlier, so adding in either Br2 or Cl2. Let's just dichlorinate. We can add in a large base. And that'll give us the two components we need to do our Diels-Alder. After we do the Diels-Alder, this gives us the vast majority of our product. We just need to make an epoxide, so throwing in MCPVA. Can get you to your final answer. Again, I'll do a pick one of the two like I did last time. Let's take a look at the last page. Then we'll take a little break. Okay. For this one, I'm supposed to draw out all four products and then use resonance to decide which one is going to be our major product. So let's start with drawing out all four products. We are going to make a 6-membered ring. It's going to be fused to another 6-membered ring. Let's start off with just our top portion here. Also, for this section of the exam, I'm going to make you guys do both of them. Just as a heads up, so you're not thrown off guard by that. All right, so our components that are in the middle, which would be these two, are going to get pushed up. These here get pushed downward. Should end up with this OMe on a wedge. Methyl on a dash, and then on the bottom, methyl on a wedge. Ethyl here on a dash. Before we fill in the rest of it, this portion of our molecule is not going to change for the 4 answers. So we can go ahead and just redraw this 3 more times. Okay, now we're filling in our dienophile portion of it. We're going to start with facing them, putting them down and keeping it in the orientation it's in. This will give us an endo product. If we take the same thing and move it to the wedge positions, we can get our first exo. Flipping it over to put the ketone on the bottom, give us our other endo. And then putting them as wedges can get them other exo. Okay, taking a look at resonance. So resonance for our first, let's do the dienophile first. It's a little bit easier. Push these electrons upward. This will generate a positive down at the bottom here. On our diene. We can also shift the electrons all the way to the bottom. This gives us charge alignment at the bottom here versus our alignment for the other answer, which would be where your negative is not attacking your positive. So this is going to be misaligned. You always want to have that negative come in and attack where your positive is. So because of that, your major product should be this endo here. Taking a look at the bottom part of this, I'm going to redraw this because I think this is harder to look at. Guess I was in a mood during this test. So let's see. Oh, I need to make this a little bigger, I think. This is kind of a trans bond here. So it should look like this. All right, from here, we're in light, doing our normal light orbitals. There are 6 of them. We're going to end up making a 6th when we're doing our product. Light, so our pattern is 1 on top, pair of 2, another pair of 2, 1 on the bottom here. I need a little more room, I think. Oh, that's way too much. They're rotating the same direction, which is counter-rotatory. Okay, it's going to push this down, this up, and then this here down. So my ethyl and my methyl are going the same direction. I'm going to make them both dashes, making the other methyl a wedge. All right, this gets us through the fall 2020 exam. Let's take this. Where's the second methyl coming from? So the ethyl's coming from here, and then the other methyl's coming from here. Is that what you mean? Or did I draw an extra methyl on there?
I think you might have added another one.
Yeah, I see it. I see it. That one doesn't need to be on there. Okay. All right. Let's take till 10:10, come back, and then take a look at the spring exam. All right, let's do some naming. So for this first one, taking a look, we got a cyclohexane. We got this ethoxy group and a methyl group. Realistically, two different ways you could number this be either 1, 2. Let's zoom in on these. Either 1, 2, 3, 4, 5, 6, or numbering it the other way. 1, 2, 4, 5, 6. Substituent numbers are going to be the same, which means we're going to go down to alphabetical. This is an ethoxy versus a methyl. E comes before M. We're going to number it the red pathway. Oops, that's not the erase button. All right, so we got a cyclohexane. We've got 1 ethoxy, 2 methyl. Let's do some RNS. Highest priority would be here. We've got 2, 3. This is going clockwise. It should be R. Taking a look at our other stereocenter. Highest priority, second, third. This is going counterclockwise. It should be S. So putting this all together, we're going to have a 1R, 2, no dash there. 2 S dash alphabetical, 1 ethoxy, 2 methyl, cyclohexane. All right, 2 ways you can write the next one. This is either an ethyl methyl ether. Or you could treat it like it's a chain. So this is your first, this would be your second. This is the longest chain you can make. You could call this a 1 ethoxy. Nope, methoxy. You got a methyl group. Ethane. Either of them is fine. All right, let's clear this. Move down to the lower portion. All right, we're clearly going left to right here. 1, 2, 3, 4, 5, 6, 7, 8. We've got an alcohol on 2, so this would be 2 octanol. We've got a bromo on 3. And another methoxy on 4. There's a lot of RNS to do. So for this 2 center, O should be your highest priority. Carbon bonded to bromine, carbon by itself. going clockwise here. That should be R. Come on. BR on this end, we've got carbon bonded to an oxygen, carbon bonded to carbon, carbon bonded to oxygen, carbon bonded to carbon. Moving over, this oxygen's bonded to a carbon, this oxygen's bonded to a hydrogen. This side should be your higher priority versus this one. We are going counterclockwise. This should be S. Last stereocenter. Pretty straightforward one. Also going counterclockwise. This would also be S. We can put this all together. We're going to have a 2R, 3S, 4S. Let's see, B comes for M, so 3 bromo. Four methoxy. Two octanol. You could also do this as octane to all, either's fine. All right, next one, it's gonna be easier to name it with just like the common naming and treating this like it's one giant substituent on here. So if I number this 1, 2, 3, 4 here, this has 3 carbons, so it's a butane.
We started with the one on the oxy because that has the highest parallel heat, right?
Also would give us the lowest number of substituents. So if you went the other direction, 1, 2, 3, 4. On the blue direction, you have a total of 6 here versus 4, 7, 9. So you get a lower number if you go starting on the oxygen.
Yeah, thank you.
Treating this like it's one substituent here. So 3 carbons will be a propoxy. So you call that 1 propoxy. 2 chloro. 3 chloro. Putting these in alphabetical order, C comes first. So 2, 3 dichloro, 1 propoxy, butane. Okay, any question on these namings? All right, we're gonna move on to the next page, which we're basically just gonna cross out. We're not gonna do NMR in this exam. Where'd my pen go? There it is. So crossing out this page, instead we'll do another mechanism page from chapter 12. Let's see, did we not do any of these? I think these all look good. So I'm not going to go through all of them. I'm going to focus. Oh, no, we didn't do this one. No, I'm second guessing myself. Nope, the rest of them look okay. So let's talk about the ones from chapter 13. we'd pick up an H here. We've got our protonated epoxide, which means when it's protonated, you're going to open on your more substituted end. So now your OH is coming over here. Because we're starting with stereochemistry, we should only get one product, as opposed to when we like add an MCPVA, you can get either. So we're doing an SN2, which means that this bottom OH is going to retain its stereochemistry. So that one should stay on a wedge. The top one is going to get flipped to a dash. They end up anti to each other. This one actually should have had a step 3 for it. Our first step is going to give us an epoxide. After which we are going to open on our less substituted position because we're in a product solution here. So Cl minus. Going to come in and attack. We're still going to get an anti-product. Although we have an achiral center on the top, so it's not going to matter. Oh, no, we don't. We have a methyl there. Okay. Methyl there. So technically, with what's drawn, you would get a negative charge here. I added in another step, just like right here, where you added in water, and that would get you to your protonated stage, giving you this product. Okay, adding in HBr with an ether lets it break it down. It only breaks it down on sp3 centers. So you're going to retain your phenol here, but you're going to do an SN2. Kick out this oxygen to give you this alkyl bromide here. Oh my God, I can't talk. The other one on this page that dealt with reactions from chapter 12. No, 13. These are chapter 13 questions. This one here, you're doing this in SN2 to form a thioether. Should give you this product. Let's pull up the exam 1 and do some of the chapter 12 ones just as a review. So going back here, I'm just going to kind of underline the ones that relate to this exam, which is quite a few of them. For this was just the fall one. All right, so chromic acid is going to do, it's our strong oxidizing reagent. It's going to oxidize anything it can. We've got 2 protons coming off of both of these positions. They can both be oxidized twice. We have a tertiary one, which can't be oxidized at all. So this should give us this fully oxidized compound. SOCl2 is going to take a alcohol, turn it into a chlorine. It's an SN2 reaction, so it's going to flip the stereochemistry. So we should end up with a wedge on the left and then a dash on the right for this. H2 is going to reduce absolutely everything. This MCPAV and H3O plus is always gives us anti-addition of alcohols. This is also covered in chapter 8, but it's also on here, so I figured I'd just touch on it. All right. Do the PCC first one. So PCC is our soft oxidizing reagent. In this case, there's only one H on here anyway, so it doesn't really matter. This is going to oxidize us. To a ketone. Lastly, taking a look at this, we have LAH, which is going to reduce everything but double bond or but alkene double bonds. So we're going to end up breaking this bond as well as reducing over here. Let's start off by just drawing the 6-membered ring that is remaining the same. With its new alcohol on it. We're going to break the bond over here and reduce to an alcohol. As well as leave this one over here. Okay, so those are the reactions from 12 that are on this exam 1 sheet here. This was, I believe this is the fall. Yeah, no, this is the spring. Let's find this fall one, see what that looks like. That's the one I just did. All right, so we've got a lot of reactions here we can take a look at. Let's start with our oxidizing reagents. So we've got 1 H over here, 2 H's over here. So we can get a ketone and a carboxylic acid out of this oxidation. That'll be the fully oxidized form of that. NaBH4 is our soft reducing agent. It's only going to reduce aldehydes and ketones, which means that it's only going to touch this center and this center here, meaning we can draw the rest of the molecule as is. And end up with alcohols in these 2 centers. SOCl2 does an SN2 to flip the stereochemistry of this to an alcohol. Or sorry, to a chlorine. So we're flipping from a wedge to a dash. We've got a couple of epoxide openings. This first one is a parodic, so it's going to open on the left substituted end. We're going to retain our stereochemistry on the center we didn't attack. And you get the opposite stereochemistry on the one we did. Forming a ether on this next one. We've got our strong reducing agent on this with LAH here. So this will reduce both the ketone and the carboxylic acid now. MCPBA will make this into an epoxide. HBr will open on our more substituted end. And lastly, PCC is going to do a single oxidation. So even though we have two protons here, we're only going to use one of them. It's going to make a ketone and an aldehyde. So different from our answer that was up here. To give us this product. All right, let's return to the spring exam, see what we need to cross out. I'm going to do one mechanism from chapter 12 and then probably call it from there. So let's go back to the spring. Let's see. I know we at least didn't do this one. Rest of these should be fine. I'm going to tell you guys not to worry about this bottom one. Even though you technically know how to do it, but it's a pain. I'm not going to ask that hard of a question. And then this one is the same as the one we did before, so this one should be fine here. All right, let's go back to a chapter or exam 1 mechanism, do that, and then we will call it for today. Nope, not that. Where are you? All right. Taking a look at this Grignard reaction here. So our Grignard gives us a lone pair. Yep, there's office hours from 11 to 1 today. This lets us do an attack at this center. We'll want an oxygen there. I'm only going to give you one mechanism to do, so it won't be doing two of them. because we're only going to do one mechanism. It's going to be from chapter 12. From here, we can kick out this oxygen. This is going to give us back a ketone. Another equivalent of our Grignard can do an attack. And then finally adding in water lets us protonate these. To give us our final answer here. So, bit of a review on these Grignard openings. You can do a double addition with an ester, and then ketone will just do a single addition. Okay, I am gonna stop here. Are there any questions from you guys? Office hours will be from 11 to 1 today, so you also are more than welcome to ask the questions there. Yeah, so there'll be a missing reagent page like the ones we went over today. It's just going to be a short one, like a half one again. All right, if not, I will either see you guys in office hours or tomorrow during the exam. There will be no recitation on Wednesday.